Hi, welcome back. I'd like to review the HAZOP analysis method. Part of the attraction is the name. What kind of a name is it? HAZOP. It's hazards in operation, or hazard and operability. This particular thing is the UK Department of Defence standard. It didn't originate with the Department of Defence, but where I came across it, it was within the Department of Defence. And I'm not entirely sure how I managed to get hold of a UK Department of Defence standard, but you can search for it and you'll probably find it as well. It is UK Defence Standard 58. It is a very formal inspection method for any design, any architecture. It's checklist based and it's very useful for life-critical real-time systems. My understanding, which I gained when I first looked at it, was that this arose out of an inquiry into an explosion at a chemical refinery in Wales. The inquiry went into how did this happen, and how could it be prevented? And the method of prevention, they found, in fact, that the accident was a flawed design for the refinery, or the chemical refinery. So it was a fault in the design. And the question is, well, how could we find a fault in a design? And this was the result. The scope and applicability of this standard is recorded there. It's intended to be used by those who, in conforming to the requirements of this standard, choose to use the HAZOP study as part of the method of hazard analysis. More generally, it's a self-contained guide to carrying out a HAZOP study on any system, including, as I've seen, an example of one on a helicopter flight control system. It's a detailed guide for those who need it and a reference for experienced HAZOP practitioners. There's a great deal more information there that tells you more about what it's intended to do. It is rigorous. It's probably exhausting to do, but if you are dealing with things that can kill people if they fail, then probably it's a pretty good idea. The general requirements of a HAZOP study. A number of HAZOP studies carried out over the system life cycle can contribute significantly to achieving the level of confidence required in a hazard identification process. As I said, if you have a chemical refinery about the place somewhere, it's going to be there for decades, and you want to be reasonably well assured that it's not going to blow up. Okay? So you're probably going to spend a fair bit of time looking at this thing. Similarly, any life-critical system, you really want to check, can this thing go wrong? And that's what it's all about. It's not concerned about can it go right. We assume it can go right. What this review method is concerned about is can it go wrong? Now the overview, like most of these review methods, there's an initial period, initiate and study the study and define the scope and the objectives. So you have to decide what it is you're going to review. Are you going to review only the architecture of this little part, or are you going to review the architecture of the whole part? Is it in draft, and so you shouldn't go past these restrictions, or is it final and we can go and analyze the whole lot we want? So scope is something you really need to sort out. You plan the study, then you carry out a series of study meetings in which the team selects a connection or a component, identifies each entity, identifies the attributes of each entity, investigates deviations from the design intent by applying guide words and attributes, investigates for each one, and documents the results. Right? Now that's a very quick run through of what goes on, and we'll go through it more slowly. The activity. It's a rigorous and systematic procedure shall be used to investigate the possible deviations of attributes from their design intent. Now this essentially means you have a look at some component in the architecture and you determine what it should do. Then you look at the guide words, which I'll review in a moment, and see, can this thing get it wrong? Now, guide word is a word or a phrase used to describe deviations from the circumstances this thing ought to find itself in. And the role of the guide word is to prompt and to focus the study, not to compel. It's possible to say, well, that's ridiculous. Now, here are the guide words. Now, bear in mind, we were thinking in terms of signals in. Now, the chemical refinery, it's chemicals coming in. Or some signal to a valve or something like that. So we have this question, a guide word is no. Now, what happens if no data or control signal is passed? So if you're looking at a control system particularly, and you're looking at what does it do in these circumstances, what happens if it doesn't get the signal? Will that go wrong? What happens if more data is passed than you intended? Telecommunications, we go with this one. You're expecting a record of a certain length and you get a record of double the length. What are you going to do? Less data. You're expecting a certain amount of data and you don't get it all. What are you going to do? How does the system handle it? As well as, so you get 2 signals or 3 signals or multiple signals. And you want one and you got several. How are you going to handle it? Will this system handle that? Part of. So the data or control signals are incomplete. Reverse. Normally in software is not particularly relevant. We don't tend not to get reverse flows in the system. And you could imagine in a chemical factory or something with physical flows, you might get it reversing. Other than data signals are complete but incorrect. Right? So we've got a signal. We expected a signal. It's the right type of signal, but it says the wrong thing. So somebody's lying to it. Early, the signal arrives too early with reference to clock time. So we're expecting a signal out of, bear in mind, we're talking about a real-time control system, and we're expecting a signal at a certain time. It arrives, but it's far too early. Is that going to matter? Or late. It arrives, but it's too late. It's fun to think of these things. Before, the signal arrives earlier than intended within a sequence of things. So we're expecting, say, a control signal and some data, and we get them in the wrong way. Is it going to matter? After, same deal. We've got a control signal and data, or control signal and several data, or several control signals and several data, and they're in the wrong sequence. Is this system going to handle it? As you can see, it's a great deal of fun to try and think of these things. Is this going to matter in this software system? And it's very, very tempting in a software system to say, software, it doesn't happen. Maybe. Be quite good to think about these things though. So in summary there, and I've deliberately got a picture of a cockpit of an aircraft because this is the kind of thing you're dealing with. They're up at 30,000 feet, and they're miles away from anywhere, they're over the sea. You can't sit there and debug the thing, right? We want to check it out before the event, and this is the architecture, so here is a good chance to try and get it right. The summary then, the HAZOP analysis is a formal inspection of an architecture requiring formal documentation. We are talking about life-critical systems, and this HAZOP analysis will form part of the verification record for this system, so it's important. It is a checklist-based system. It concentrates on the flow of information through the system, and particularly through the components of the system. Each architectural element is checked using the words on the guide list, or the guide words on the list. It is rigorous. It is intended for life-critical systems. And I can imagine the exhaustion of this particular method, but it is rigorous.